Hi guys, welcome back. So in this video we'll be discussing about the registers. So register is a class of sequential circuit with no combinational circuit required for the basic functionality, and the registers are capable of storing any binary information in it. And if you take this, the basic building blocks are flip-flops. Since we know that the flip-flop is capable of storing one bit of binary information in it, either a 0 or 1, and it is considered as a binary cell. So a register is a group of binary cell which is capable of storing an n-bit binary data in it. And so since every cell is capable of storing one bit, so an n-bit register will contain n number of flip-flops. And the purpose of register is for data storage basically. So it essentially employs d flip-flops for the implementation. And this is a class of synchronous clocked sequential circuit. So means that all the flip-flops are clocked simultaneously from a master clock source. And with few gates, the functionality of the registers can be controlled. Okay, so regarding this functionality control, we'll discuss in detail in the later part of the slides. So, and the register classification, if we consider, based on how the data is loaded into the register and how it is retrieved from the register, based on this, the registers are classified as parallel in parallel out, parallel in serial out, serial in serial out, serial in parallel out configuration, and then the shift registers. Okay, so parallel in means if we have n bit of information, if we are able to store all the n bit information parallelly simultaneously into the register and we can read it simultaneously, then it is referred as an parallel in and parallel out configuration. If I see that parallel in serial out configuration, we can load the data, all the n bit information parallelly into the register, but if you want to read the data, you can do it bitwise, then it is an parallel in serial out configuration. Then we have that serial in serial out configuration where the data is given data input is given bitwise and the data is read bitwise. And the next configuration is serial in and parallel out where the input data is loaded serially and then it is read parallelly from all the flip-flops stored in this. Shift register is another is a class of the serial in serial out configuration. It is basically performs the data shifting operation, which may come under any one of these four categories. Okay, and the key points what we need to consider here is, as long as the clock pulse is positive, the input data ix is not loaded. Okay, the ix is loaded only when the clock pulse is positive, and then once the clock is observed, then the data is transferred to the q output of the flip flop, which is going to be the output, that is the data stored in the register a. Suppose if there is any change in input data and the clock is equal to 0, then the change in input is not going to affect the data stored. So these are the key points to remember to understand the function of the register. Okay, the thing is, the input will be the input will be loaded into the register when the clock is positive, or that is your during the positive going edge of the clock pulse. And once the flip-flop senses the positive edge clock, then the data whatever available at the input of the flip-flop is transferred to the output q output, and the same data is retained in the flip-flop. If suppose if the clock is 0, means that if it is a negative edge or if the clock event is not sensed, then the data whatever is stored in the data will remain unchanged. So this is an it's a schematic of an simple parallel in parallel out register. It comprises of three flip flop, which means that we can store 3 bit of data in this register. We can observe the register is constructed using a D flip flop, and you see the clock inputs. All the clock inputs are tied together and it is connected to an common clock source. And you see this, it is an positive edge triggered flip flop, means that the change in the input data, the change in the input will be transferred to the output during the positive rising edge or during the positive edge or the rising edge of the clock pulse. So here, if you see the functionality at time t equal to 0, so let us consider at time t equal to 0, we are loading the information 1 1 1. We want to load this information to this. So at time t equal to 0, we are applying the inputs as 1 1 1. Now we want this inputs to be transferred to the outputs QA, QB, QC. That is our output lines here are A0, A1 and A2. So now when this will happen? So once after applying the inputs, and then if the clock pulse is observed to be on positive edge, then so let us assume initially the data out, that is my A2, A1, A0, and this let it be I2, I1, I0. So once the positive edge of the clock is being applied, then the outputs, the Q outputs of flip flop will change from 000 to 111. Okay. Now if there is any input change that happens here 010, in the absence of no clock, that means that no clock is being applied, the data will be retained as such, the data will not be changed. So this is what the basic functionality, but in real time this will not be. Why? Because this clock signal will be from a global generator, that is from a global circuit which will continuously deliver the clock pulse like this. If you take in any system, your master clock will produce an clock pulse continuously starting from time t equal to 0 to infinity. So if that is the case, any change in the input will be reflecting in the output during the next positive edge of the change of input. Okay, so to avoid this only, we need some circuitry to retain the data. Okay. So this is an circuit of an parallel load register with load control. So before that, let us have some discussion about the global signals over here. You can see here this is an 4-bit register. A1, A2, A3, A4 is the data stored, and it is constructed using D flip-flops. And the D flip-flops, if you see all the flip-flop, the clock inputs are tied together and it is connected to the global clock pulse. And whatever there in this triangular signal is referred as an buffer. Buffer is used for data refreshing. Okay, the functionality, if you see, it is used for refreshing the data. But logic wise, if you can logic wise, it is used for buffering the data. But if you see that technically, what it does is it is going to avoid overloading on the clock source. It's going to avoid overloading on the clock source. Okay. And then we have another input, so called the clear input. Clear input is basically an active low input. So if you take a clear input, it's an active low input category. That is, if clear is equal to 0, if clear signal is equal to 0, then irrespective of the input, the Q output of the flip-flop will be made 0. Okay, so this is an asynchronous input, means it doesn't wait for any clock pulse to arrive to change the output, irrespective of the clock pulse whether it is present or not, or any transition whatever it is. If the clear is activated, then all the Q outputs of the flip-flop will go to 0 by default. Okay, and if you see this clock pulse, again, as I said earlier, the clock pulse will be continuously available from the global clock generator, and we cannot limit it. Okay, but we want to store the data in this D flip-flop for certain period. So for that, what we are doing here is we are introducing an control signal over here called the load signal. So again, we are using two buffers over here. See the triangle one is a buffer, and the triangle one with the bubble is referred as an invert buffer. So what it means, for buffer, whatever is the input data, the same will be available at the output. But if you take the invert buffer, the complement will be available at the output. Suppose if my input logic is 1, then the output will be equal to, the output logic will be 0. Okay, so for an example, if you see here in this clock pulse, I have drawn the clock pulse with the positive edge, but the output will be a negative edge. So it will be from 1 0 1, like this. I'll get a output from this. Okay, so if my clock input here, if it is negative, I'll get a positive edge over here. Okay, so if we consider here in this case, if so let me take it. So if I consider here, if my input is a negative going pulse, then the output will be a positive edge pulse. So this is the logic over here. And similarly, if I consider the load, if load is equal to 1, here I'll get 0, and here I'll get 1 again. Now you see this, the input to the D flip-flop is from a OR gate. The OR gate receives its inputs from two AND gates. And to the AND gates, the input, if you see here, again this is an load, and this is input I1, and this is complement of load, and this is your output A1. Okay, so what my logic here is, when load signal is equal to 1, then the input I1 must be passed on to the D flip-flop. If the load input is 0, then whatever the data previously stored, that must be buffered. Okay, that is the concept here. So let me consider first my load input is equal to 1. So if my load input is equal to 1, here it is equal to 0. So my load bar is 0. If we take the output of this AND gate, 0.A1, so we know this 0 AND with anything is 0, and here 1 ANDed with I1 will be the I1. And when it comes to this OR gate, 0 plus I1 is I1. So when the load signal is equal to 1, then I is passed to the D. So on the event of clock, the positive edge, this I1 is transferred to A1. Okay. Now if you take the second case, what happens if load is equal to 0? If this is equal to 0, load bar is 1, and again here it is 0. I'll take the same thing with this here. So here it is 0, here it is I, here it is 1, and here it is A. Now if I consider this, 0.I is 0, 1.A is A, 0 plus A is A, so D is equal to A, where A is the output which is stored previously. So when the load is equal to 0, if further any change in the inputs I will never be reflected on the output. Only the data which is previously stored will be buffered into the system. Okay, why? Because the clock pulse will be a continuous and we cannot limit the clock pulse. Only thing what we can have is we can have the control. We can introduce some control signals. We can implement some combinations so that if the control is enabled, then you can load the data. If the control is disabled, then you can buffer the already stored information. So this is what the function of an load control in the parallel load register. Okay. Now, by means of the register, likewise, how in the previous sequential circuit design, we were discussing about how we can implement the sequential circuit using flip-flops. Okay. Now, in this case, what we are going to do here is we can implement the same sequential circuit by means of registers also. So this takes up the form of it. Okay. In generally, how we define the sequential circuit, we'll be having a combinational circuit and with a memory in the loop. Okay, and to the memory we'll be providing the clock pulse. So the memory, whatever the data stored, is considered as the state. Okay, so this is let me consider this is my present state, and whatever comes out the combinational circuit will be the next state, and it is fed back, stored along with the inputs. The combinational circuit along with the input and present state, it will generate the next state and the output. So let us discuss deal the same thing using an example. So the thing concept here is I need to design a the problem here is I need to design a sequential circuit whose state table is listed below. So if I see the state table, it was given present state, input, next state, and output, and it has two present states and one input and one output. The present states are A1 and A2, and the input is X, output is Y. So as usual in the logical in the analysis, what we do here is we'll write the we need the equations for the next state and output. We need the equation for the next state and output as a function of the present state and the input. So in that sense, we are writing for the next state equation and the output equations like this. A of t plus 1 is equal to f of a1 a2 x, means it's a function of a1 a2 and x. The present states a1 a2 and the input x. And how we are writing this summation min terms is, since it is a 3 input combination, I hope we have all the 8 input combinations present in the state table. So now all 8 combinations with 3 bit means that the table is complete. So I can consider this as a min term 0, and this is corresponding to min term 7. So totally 8 combinations are available. So this is for 0, 1, 2, 3, 4, 5, 6 and 7. So A1 is 1 for the min terms 4 and min term 6. So that's why I'm writing summation m of 4 comma 6. And for A2, if we observe, A2 is equal to 1 for decimal 1, decimal 2, decimal 5 and decimal 6. So that's why I'm writing the summation min terms of 1 comma 2 comma 5 comma 6. And similarly, if I want to express the output y of t plus 1, then this is equal to summation min terms of 3 comma 7. So in this way, I identified this is the logical function for the next states and the output. But I need this in the form of a Boolean expression for the real-time implementation. So from the table, how to get the equation? As usual, we'll go with the K-map procedure. So we'll be taking the K-map for A1, A2 and Y. So the mapping sequence is just shown here. Previously we'll have it in the horizontal form. Now I taken in the vertical form over here. So 0 0 0, the 0 1 2 3 6 7 4 5 like this. So initially we had this one, that is 0 1 3 2 4 5 7 6. Now in this case it is simply an ulta of it. 0 1 2 3 6 7 4 5. So in this way we are taking in a vertical orientation. That is what the this template explains how the data is mapped. So how we have done the previous case, the mapping and all, the same way mapping and done, grouping is done, and we are expressing a1 next state of a1 as if for this group a1 and x bar. Okay, a1 and x bar for a1 of t plus 1. And if I consider a2, I'll get here A2 x bar x A2 bar. So which is nothing but A2 XORed with x. And if I consider y, then it is A2 x. So A2x is a y of t plus 1. Since we got all these expressions, then we can implement this using a logic diagram. And if a register, how it is being represented, the register is represented as a simple block over here. Okay, uh, because register is basically a D flip-flop. Whatever is the input you are applying, the same will be the output. So I am taken here, what is A of t plus 1 is A1 x bar, and A2 is A2 XOR with x. And if I consider the output, output is A2 into x. So I'll get y is equal to A2x. A2 of this one is t plus 1 is A2 XORed with x. And if we take this A1, this is equal to A1 x bar. So A1 present state is next state is given to the again the register over here, the input x. So like this, we can implement the sequential circuit, any sequential circuit, if it was given in this state table form into this logic circuit over here. Then coming to the shift register. So shift register is a memory which is capable of rotating the data. So rotating the data in the sense, either the data can be rotated in from left to right or in the direction of right to left. Okay, and so it is used for data shifting operation. Practically where it is being used, practically these shift registers are used for generating the physical address of the memory in the computers. Okay, so now if you take it, how the shift register is implemented. In if you take the shift register, the flip-flops are connected in cascade. Cascade means the output of one stage will be the input for the next stage. Okay, so if I consider here, it is basically an example of serial in serial out type of shift register. Means that the data input is going to be serial, bitwise the data is being transmitted from the input, and the same bitwise the data is received at the output. So this is going to be the serial output pin, and this is going to be our serial input pin. Okay, and if you observe the clock pulse, all the flip-flops are clocked simultaneously, and it is a negative edge triggered type of flip-flop which has been considered over here. Okay, and if you see this, all the clock pulses, all the flip-flops are clocked synchronously from a global clock source, and a simple form of shift register with flip-flop is shown here. And here if you see this, here lies your input and here is your output. Means that the data propagates from left to right in a bitwise manner. Bit by bit it is transferring from the data the data has been transferred from left to right. Suppose if the same register can be made to operate as a shift left register, how it is being done is simply we have to take the mirror image of this. Mirror image of this means then it becomes Q, then it becomes D. If I am taking in this condition again, this forms 4 3 Q2 D2, and here Q1 D1, and in this case this is going to be your input and this Q is going to be the output. So if I follow in this way, then the data is transferred from Q4 to Q3, then to Q1, then Q2, then to Q1. So the data travel direction is in the from right to left. So this configuration is referred as a shift left register. But now we are considering the working of a shift right register. So we can consider, we can understand the concept of shift right register by means of an example. So initially let me consider Using a clear input, I cleared the outputs of Q outputs of all the 4 flip-flops present in the shift register. So initially all the data is 0. All the Q outputs are 0. And what I do here is I am just changing the data from 0 to 1. The moment when I change the input data from 0 to 1, the Q outputs are not affected. What is the reason? The flip-flop is a negative edge triggered flip-flop. So the flip-flops will change its output when it receives a negative clock. Okay. So this is the clock pulse. This is the clock pulse. And this is the first negative edge which is being sensed. See, before the negative edge, the data stored in Q1 is 0 and the same data is available in D2. Okay. And if you see, once the negative edge is sensed, then the input IE is transferred to Q1. So Q1, now the data is changing from 0 to 1. Since all the flip-flops are clocked simultaneously, if you see for Q2, at the instant when it is receiving the negative edge, the data present in Q1 is 0. So my Q2 remains 0. Since Q2 value is 0 also, my Q3 value is also 0. Since Q3 is 0, my Q4 value is also equal to 0 at the after first negative edge of the clock. Now when it comes to the second negative edge, in the second negative edge my Q1 is 1. So once it's after crossing second negative edge, the Q2 will now change from 0 to 1. If we take Q3, the instant at which the negative edge arrives, at its input 0 is available. So even after the second clock stage, Q3 will remain 0. The same way for Q4 also. Then if you consider here it is 1 1 0 0. Then at the third negative edge, if we consider at the third negative edge, Q1 is 1, Q2 is 1. So now what happened is, once after third negative edge, my Q3 will now change to 1. Why? Because Q2 is equal to D3. So after the negative edge, the Q3 will change to 1. But still, my Q4 will be 0. Why? Because the instant at which the negative edge arises, at that particular point, my Q3 is equal to 0 and hence D4 is equal to 0. Therefore, Q4 is equal to 0. So after fourth negative edge, again, since Q3 is 1, the same information is transferred to Q4. You can see here as the time progresses, at the end of 4 clock cycles, all the Q outputs of all the 4 flip-flops will be equal to 1 1 1 1 logic. So for an n-bit flip-flop, it requires n clock cycles for loading the data completely into the register. Now again, for an example, I am just changing my data from 1 to 0, which is happening some in between instant of the negative edges. See, since the data, even the input has been changed at some random time between the negative edge, the outputs of the flip-flops will not change. Why? Because it has to wait for the negative edge. So at this point, at this time, the input is changed, but you see this, the input is applied to D1, but Q1 will not change till the next clock negative edge of the clock. Once the next negative edge is arrived, then the Q1 will shift to 0. But before the instant of this negative edge, Q1 is equal to 1. So my Q2 value is equal to 1. So Q3 is 1 and Q4 is equal to 1. After the second clock edge of after changing 0, my Q1, Q2 will go to 0, but Q3, Q4 will remain at 1. After the end of third clock pulse, my Q3 will become 0, but Q4 will be equal to 1. At the end of fourth clock pulse, all 4 Q outputs will be equal to 0. So you can see here again for the the 1 to 0 transition, again it took 4 clock cycles to make all the data to be loaded into the register. And the data access is your Q4. Through Q4 only we can take the output data. See, at time t equal to 0, we applied the input equal to 1. So at the end of 4th clock cycle, I got the output at Q4 is equal to 1. And similarly, at some random time, we change the input from 1 to 0. After end of 4th clock cycle, at the output, we are receiving the data. So the data, if you see from the circuit, it is propagating from Q1 to Q2, then to Q3, then to Q4. So the shift is from left to right. So that's why it was named as an shift right register. Okay. Thank you.